This presentation, I'll be discussing Kesten's incipient infinite cluster for the three-dimensional metric graph Gaussian-free field and for the Villain model. To begin with the presentation overview, I'll be introducing the construction of the metric graph Gaussian-free field, or GFF for short, from the typical or regular GFF. And in doing this, we'll want to introduce quantities relating to arguments of Ding and Wirth, which pertain to the exploration martingale, and in particular, how properties of this martingale can be expressed with a harmonic measure that is only dependent along a finite volume boundary. And with these quantities, we pivot towards other open questions at the author's ways, in which one of them relates to the construction of the metric graph GFF incipient infinite cluster in 3 dimensions. And finally, we'll also incorporate the Villain model into our discussions from another open problem that was raised in the October 2022 work of Dubeda and Falconet. And one primary point of reference that we're going to be using in this presentation is the following paper, which is titled Percolation for Level Sets of Gaussian-free Fields on Metric Graphs by Professor Ding and Dr. Wirth, the first version of which was available in 2018. And this paper is important for us because it's going to show us and demonstrate to us how we can think or approach constructing the incipient infinite cluster for the metric graph Gaussian-free field in 3 dimensions. So this is the first item that we're going to begin with, namely constructing the metric graph extension of the Gaussian-free field in 3 dimensions. The first things that we need are that we need some underlying graph, which is G, which is dependent upon some vertex and edge sets. And then on G is equal to ZD, namely the D-dimensional lattice, for D greater than or equal to 3, we can look at the family of continuous time simple random walks, in which are denoted with S of t, where t is a natural parameter corresponding to the time. And this collection of simple random walks have transition rates 1 over 2 to the d. And the GFF essentials that we need to begin defining the metric graph GFF from the regular GFF is that we have to keep in mind that the regular GFF is given by a mathematical object which has a mean 0 and covariance given by the Green's function. So what this means is that if we fix any two vertices u and v belonging to the set V of our underlying graph G, the covariance function, which is given by the expectation of phi u phi v, where phi u and phi v denote the Gaussian free field corresponding to the points to the vertices u and v that we choose from our vertex set, this covariance, which is given by the expectation term, is equivalent to the Green's function between the points u and v, which in itself is equivalent to the expectation with respect to the law of p of u of the expected number of times that the simple continuous time random walk will hit v if it starts from u. And in the integral, we integrate over from u from 0 to infinity. And we can think about how the metric graph extension would be obtained from the regular Gaussian free field. In this case, we can think to ourselves, as we've denoted in one of the items that's given in the top of the slide, is that if we start with the graph G that's given from the previous slide, we can fix some 2 points u and v in the vertex set, and we can lift to the metric graph, which is given by a tilde of G, which can be expressed as a union over compact intervals I of E. And the compact interval is the length of whatever dimensionality the underlying graph is. If we're in ZD, the length of each one of the compact intervals that we're taking the union with to form the metric graph extension from the regular graph would be of length 3 for the 3-dimensional metric graph Gaussian free field. And what we want is that we're going to take these 2 points u and v, and we're going to still be looking at them within the lifted vertex set, of which the graph tilde of G is dependent upon, because we want to also have, just as the regular graph G that we use for defining the typical Gaussian free field is dependent only on V and E, the lifted graph will also be dependent on some lifted counterparts V twiddle and E twiddle. But besides the underlying graph structure that we have to look at, we also have to be looking to lift fields to the metric graph, which is to say that we would start with some 2 components for the Gaussian free field, phi u, phi v, and their counterparts in the metric graph extension to obtain the metric graph Gaussian free field in 3 dimensions would be given by twiddle phi of u and twiddle phi of v. So we're mentioning now and transitioning from the regular Gaussian free field to the metric graph Gaussian free field because we want to think about how the covariance and other qualities of the metric graph Gaussian free field would be different from the typical Gaussian free field, and how this would inform our construction of Kesten's incipient infinite cluster, which is one of the open questions that Professor Ding and Dr. Wirth raised in that paper that we had introduced at the beginning. So we can look to the covariance. The covariance, as we had mentioned in the previous slide for the regular Gaussian free field, is given by this expectation of phi u of phi v, which is equivalent to the Green's function between the points u and v. So we can think about if we were to take this covariance for the regular Gaussian free field, how would we obtain, or how would one obtain the covariance function for the metric graph Gaussian free field? And this is very much related to the two questions that we have here, in which we want to think about how does the covariance change when we pass to the metric graph extension, and how does this appear in quantities that are introduced for three-dimensional level set percolation? So we're also going to define level set percolation as some related quantities of the exploration martingale and other things that Professor Ding and Dr. Wirth use in their paper. And to first answer the question that we had raised in the previous slide with regards to how would one define the covariance function, or which plays the role of the Green's function in the regular Gaussian free field for the metric graph Gaussian free field, we will make use of one paper that's given by Lupu, which was first available in 2014, and it's titled From Loop Clusters and Random Interlacement to the Free Field. And he provides us with an expression for the Green's function for the metric graph Gaussian free field that's expressed in terms of the Green's function for the regular Gaussian free field. But there are some different parameters that show how the construction of this mathematical object for the covariance of the metric graph Gaussian free field is a little bit different than the one that I gave you for the typical Gaussian free field that everyone sees. So what we first have to do is that in the first line, we need to define some vertices u1, v1, and also u2 and v2, which belong to the lifted vertex set, which is one of the components from the lifted metric graph extension that we had mentioned previously. And also what we can do is that we can take edges between the vertices and points that we fixed in the previous line above. Namely, we want to look at E of u1 and v1, and also another edge which is dependent, which has the endpoints u2 and v2. And then we'll fix some points w1 and w2, which are some points that are within the edges that we gave in the previous slide, in addition to finally defining the quantities r1 and r2, which are given by the absolute value difference between w1 and u1, in addition to the absolute value difference between w2 and u2. So these are the quantities which I'm going to rephrase when we introduce the covariance function for the metric graph Gaussian free field in the next slide. But this is just demonstrating how certain properties that one would expect to hold for the Gaussian free field also apply and can manifest in slightly different ways for its metric graph extension in 3 dimensions. And from this choice of parameters, as we have been mentioning, we've been looking at the following quantities. For one, we introduced the vertices. We introduced the edges corresponding to these endpoints, as we have been mentioning, in addition to the points on the edges, which are given by W1 and W2. And finally, the quantities R1 and R2. So then we can look to define the Green's function for the metric graph extension, in which we want to look under the same expectation of u, in which covariance function, which is given by Green's function between w1 and w2. However, what I'm sure anybody can see immediately is that this superposition, which is given for the covariance function for the metric graph extension, is quite a bit more complicated. We have to keep into account whether the Green's function is evaluated at an edge or at points of edges. It's the Green's function that is for the metric graph Gaussian free field is different from the covariance or Green's function for the regular Gaussian free field, because these parameters W1 and W2 that we pass to the covariance function for the metric graph Gaussian free field G is a little bit different, because these are points on edges and not exact vertices themselves where the continuous time random walk begins and should end. So what we can basically look at to further decompose this Green's function for the covariance or the covariance, which is used for the Green's function of the metric graph Gaussian-free field that we have been mentioning, is that for any of the arguments which are involved, which are dependent upon the Green's function for the typical Gaussian-free field, we just look at whether we include a prefactor which is either dependent upon R1 and R2. We can see that if we take, as given in the second term that's given in the covariance in the Green's function for the metric graph Gaussian-free field, that if we look at g of v1 and v2, which is the Green's function between these two vertices that we fixed from the previous choice of parameters that we have been discussing, we just multiply this term of the Green's function by r1 and r2. Whereas if we look at another term for the Green's function that's right next to it in the superposition, we would have g of u1 and v2, which is demonstrating that if we choose one vertex which is from one of the points, as well as another vertex v2 that's given on another of the points, we multiply the Green's function by one prefactor which is dependent upon r2 and another prefactor which is dependent on 1 minus r1. So this is just really demonstrating how one can construct the metric graph Gaussian-free field covariance function, and how different terms of it relate to the arguments that we pass and evaluate the typical Green's function for the Gaussian-free field upon. And from the metric graph covariance, we can introduce other quantities to motivate the construction of the incipient infinite cluster. So for one, we'll need a finite volume of length r, which is to say we can fix some r greater than or equal to 1, and we're going to look at v of r, which is the intersection of the compact interval with zd. And we can also set heights across which the metric graph has to exceed some height h, which is given by the following set. Because we want to look at because we want to make use of certain properties of the exploration martingale in critical level set percolation for the metric graph Gaussian-free field in 3 dimensions, we can define a set E twiddle, which is dependent upon the height h of the Gaussian-free field as well as the length of the finite volume n. And these are simply the vertices within the lifted metric graph for the d-dimensional lattice in which the Gaussian-free field exceeds some height h. And finally, we'll also want to make use of a graph distance, which is given by the following definition. This also coincides with other definitions in the literature and terminology in which others call it the chemical distance, in which it's given by an infimum of script d of nh of uv, where u and v are 2 points lying in some sets a and b. And we know that if this distance is finite, this communicates that u and v are connected, while if the distance that's given from the metric or the graph distance is infinite, u and v are disconnected. So these quantities so far are very much defining classical things that anybody looks at when we consider different type of percolation models. But the thing is that we're inserting a very specific dependency upon the level set percolation occurring as to whether the height of the metric graph Gaussian-free field exceeds some threshold h. And from these quantities that were given in the previous slide, we can define the law of the metric graph GFF by specifying the following 2 items. First, we'll need to specify 4 parameters, which is given by h, which is some real parameter, as well as 3 other parameters, alpha, beta, and gamma, which are strictly between 0 and 1 in ascending order. And we can incorporate these parameters into the probability measure that's given for the metric graph Gaussian-free field by this quantity. We want to look at the probability, which is the law of sampling some realization of the metric graph Gaussian-free field from the construction that we've given, which builds upon the typical Gaussian-free field. And this probability measure is dependent upon alpha, gamma, which are given in the superscript, while in the subscript, the probability measure also admits a dependency on the length of the finite volume, which is given by big N, as well as the height threshold that we use to enforce that the metric graph Gaussian-free field exceed. And one main result that appears in the paper due to Professor Ding and Dr. Wirth is the following. So we want to provide one main result regarding level set percolation probabilities, which is providing with us with a poly-logarithmic upper bound that we'll describe. So in this theorem, that we have appropriated from their work to describe how the incipient infinite cluster for the metrograph Gaussian-free field in 3 dimensions can be constructed, we make a similar use of parameters that we had mentioned earlier, namely that we look at some real height that we want the field, the metrograph extension in 3 dimensions to exceed, and we introduce the same parameters alpha, beta, and gamma that we introduced. And from the law of the metrograph GFF on condition upon twiddle phi n, we can introduce a crossing event, which is very much the analog of crossing events that were considered for Bernoulli percolation and several other models before the metrograph extension of the Gaussian-free field received more attention. And this crossing event is given by the fact that we want to look at a connectivity event occurring between V alpha and n to the boundary of V gamma and n, where along each one of these sites of the path, or each one of these points of the path, we want the Gaussian free field to exceed a height greater than or equal to h with respect to the chemical or graph distance dnh that we introduced earlier. So under these assumptions in this connectivity event, for any epsilon greater than 0, strictly positive, there exists a suitable constant such that the following inequality is satisfied. This inequality captures many parts of how we construct the metrograph extension of the 3-dimensional Gaussian free field, and how we can actually make use of the probability measure in the law to look at how sharply connectivity events for different for different finite volumes could be obtained. So this inequality specifically is given by the fact that we have a limit supremum as n tends to infinity of this probability, which is given by the metrograph GFF law in 3 dimensions. And what we want to look at is that as we take n to infinity, we're looking at studying the connectivity event, which is given by V alpha and n in the boundary of V beta of n with respect to the chemical or metrograph distance. And what Professor Ding and Dr. Wirth are showing to us in this statement is that we can have, as we take n to infinity and encounter as we take n to infinity and we're closer to encountering a larger finite volume, the probability that this distance between V alpha and n in the boundary, V beta of n, exceeds some poly-logarithmic factor, which includes a polynomial in n, in addition to a logarithmic factor of log n to the 1/4, is bounded above by epsilon. So it's basically saying that as we encounter infinite volume, as we have been mentioning, the probability of having this connectivity event occurring with the distance exceeding this poly-logarithmic factor is bounded above by epsilon. But besides this fact, which already gives us some idea about how one can incorporate the metrograph GFF law for upper bounding a connectivity event with respect to the chemical distance, we can also look at results in 2 dimensions versus those in 3 dimensions, which can also make us privy and give us some further intuition as to how different parts of the argument for constructing Kesten's incipient infinite cluster for Bernoulli percolation in 2 dimensions would differ for the metrograph Gaussian free field in 3 dimensions. And so these results are the following, for which demonstrate a dichotomy or a difference between the 2-dimensional and 3-dimensional behaviors of the metrograph extension of the Gaussian free field. And so the first result is theorem 2, which is given by theorems 3 and 4 in their paper, which is given by the following item. We want to look at exponential decay of percolation probabilities on a poly-logarithmic upper bound for percolation probabilities above the h is equal to 0 level set for 3 dimensions and greater than 3 dimensions. So basically what we have to do in many of these types of results is we have to take some sequence of heights hn which satisfy that each of the hn for n greater than or equal to 1 are less than or equal to c for some sufficient strictly positive c. And from this assumption on the sequence of heights of the metrograph Gaussian free field that we can take, we know that the three-dimensional percolation probabilities admit the two following upper bounds. So we have one specific upper bound for d is equal to 3, and another upper bound for the percolation probability, which is given for d is greater than 3. The d is equal to 3 upper bound differs from the d is greater than 3 upper bound for the percolation probability, because this exponential also has some inverse dependence upon the log n term, which coincides with the log of the log of the size of the finite volume for d is equal to 3. While for d is greater than 3, we don't have this inverse proportionality to the logarithmic factor which appears in the exponential, and instead we just have minus ch squared n. So that is to say that for d is greater than 3, the percolation probability upper bound would be dependent upon the height of the Gaussian free field in addition to the size of the finite volume across which we're measuring distances with respect to the chemical distance. And we can build upon the previous result by making use of similar assumptions in which Ding and Wirth also established the following two inequalities. So they established two other inequalities, and from what we had just been mentioning in the previous slide, no one would be surprised to also see that there is some difference in the bounds on the percolation probabilities that is given for dimension 3 and dimensions greater than 3. As one can expect, for dimension 3, instead, if we look to bound the percolation probability Pn of 0, in which instead we want to look at the probability of a percolation probability or a percolation event or a connectivity event occurring across the height h is equal to 0 of the metric graph Gaussian free field. This admits an upper bound which is given by a big C times a square root of log n over n, whereas the lower bound is just dependent on C to the reciprocal of square root of n. And this is for d is equal to 3. And instead, if we look within the similar context and the same choice of parameters that we've been introducing, for d is greater than 3, we instead have that Pn of 0 is bounded above by big C of square root of n and below by C over square root of n. So this is to say that between dimensions 3 and dimensions greater than 3, the metrograph Gaussian free field is different because it admits a different type of upper bound in which for the three-dimensional case, we'll have one upper bound which is dependent upon a log of n term, but for the d is greater than 3 case, for greater than 3 dimensions, we see that instead we have a tight inequality in which we have upper and lower bounds which are given by 1 over square root of n, but we just have a little c and a big C, which is what makes the difference. And we can complete our overview of the Ding and Wirth paper with a description of the exploration martingale. The exploration martingale is another object that they make use of and describe, which allows them to obtain the precise estimates for the percolation probabilities across the critical h is equal to 0 threshold of the metric graph Gaussian free field, in addition to the upper bound for the percolation probability across an arbitrary height threshold h. And the exploration martingale is given by the following object. So we want to look at vertices v and v from the lifted metrograph extension that we've been using to define the metrograph Gaussian free field in 3 dimensions. And the exploration martingale is specifically given by a conditional expectation MA of t is equal to the expected value of xa, which is some observable with respect to a filtration I of t, where this observable x of a takes the following term. So what we want to make use of is the fact that the Gaussian free field, because it's a distribution, it does not make literal sense, and it's ill-defined to try to define the Gaussian free field pointwise. So what we do is that we look at some type of average of the Gaussian free field in which this observable takes the form of x of a, which is the reciprocal of the cardinality of a. So it's just saying we're normalizing whatever summation we're going to take for this observable from the cardinality of the total set that we're looking at, in addition to a summation of a twiddle phi of v where v is an a. So this is the observable that we're looking to take the conditional expectation of, which is involved in the martingale, which is the expectation of xa from this observable with respect to the filtration. And the filtration of this conditional expectation is given by this quantity, which, just for convenience, I haven't included the whole definition here, but it's in our paper and it's in more detail in the upcoming work. And I naught and I of t denote the exploration sets of the random walks that are given respectively at time 0 of the beginning of the evolution and also at time little t at some arbitrary time step later in the evolution. And from our exploration martingale and bounds on percolation probabilities in 3 dimensions, we can transition towards thinking about one open question that the authors raise, which relates to the incipient infinite cluster, which is given by the IIC for short. And this appeared in one paper that was given by Kesten, in which it appeared 6 years later before his seminal work in which he demonstrated that the critical parameter of Bernoulli percolation on Z2 was a half. And in this paper, he very much builds and extends upon the knowledge that he establishes in that seminal 1980 paper and still provides some arguments and characteristics of percolation models that still remain of interest even 35 years later after the paper was published. And we can actually define directly from his paper some properties of the incipient infinite cluster and how it first applies for Bernoulli percolation in 2 dimensions. And then we can describe how some components of his argument would differ if one were to look at constructing Bernoulli percolation for an infinite unbounded degree graph instead, which is due to another 2016 work that we'll introduce. So basically, Kesten's incipient infinite cluster establishes that the 2 limits below are equal, in which one conditionally defined crossing probability that's taken at the critical parameter of Bernoulli percolation, which, as we have been mentioning, is a half from his seminal 1980 paper. He looks at the probability at this critical parameter p sub h that W naught is connected to an occupied path to the boundary of this square as n tends to infinity. And he wants to establish comparisons and actually demonstrate that these 2 limits, that this limit that's given in item 1 corresponds with the limit that's given in item 2, in which he wants to look at p of p. So that is to say that he wants to look at the Bernoulli percolation with some parameter p, but for a supercritical choice of parameters p, because he wants to approach the critical point of Bernoulli percolation that's given from a half from above. So this is just basically saying that if we look at the supercritically defined crossing probability, we're conditioned upon the fact that W is infinite, where W is some cluster, then we can establish that if we take the limit as P approaches the critical point of Bernoulli percolation, these 2 items that are given in item 1 and 2 should be equal. And to answer the open question for construction of the incipient infinite cluster of the metric graph GFF, we pursue the following steps. So we have to identify the critical height threshold of the metric graph GFF. And fortunately for us, this is already established in the same paper due to Lupu from 2014 that we had used to establish the structure of the covariance function for the metric graph Gaussian-free field, in which he draws our attention to the fact that there is a critical h is equal to 0 threshold for the metric graph Gaussian-free field. So this is already very much encouraging for us, because if we want to think about how we would be able to make use and appropriately apply Kesten's construction of the incipient infinite cluster for one model, which is given by Bernoulli percolation, for the metric graph extension of the Gaussian-free field instead, we have to identify some dependence of each one of the models, which would depend upon how Bernoulli percolation has this critical point PC, which coincides with the half, and whether there would be any types of characteristics that we can manipulate and make use of for the metric graph Gaussian-free field. And so this is just what we're saying we want to do. We want to define two limits akin to those provided by Kesten in his arguments that were first executed from the 1986 paper, and we want to discuss assumptions of the streamlined presentation of Kesten's 1986 arguments that are provided by Basu and Shaposhnikov in 2016. So the 2016 argument due to Dr. Basu and Professor Shaposhnikov draws our attention to the fact about how different components of the construction of the incipient infinite cluster would differ depending upon the assumptions on the graph. So they still construct the incipient infinite cluster for Bernoulli percolation, but on a slightly different graph. And Professor Ding and Dr. Wirth in their paper mentioned that this streamlined presentation of the construction of the IIC could be applied, or is of interest to apply it to the three-dimensional metrograph Gaussian-free field. So we're seeing many different models that are coming into play in connection with each other, in which we can see that we begin with Bernoulli percolation, and then we can look to try to establish some comparisons with the Gaussian-free field and with its metrograph extension. So before proceeding, we introduce the single ingredient, which we need for defining some analogs of the two limits that Kesten demonstrates are equal for the IIC and from his 1986 paper. And in particular, we want to look at definition 8, which is saying that cylinder events are a function of the height of the metrograph Gaussian-free field. And we need cylinder events because cylinder events are introduced originally for the arguments that are given in Bernoulli percolation, which are events that are precisely dependent upon only finitely many vertices. And this notion transfers over in the case of the metrograph Gaussian-free field because we need to look at the height, which is associated and attributed to every one of the vertices in our ambient lifted graph that we lifted to when we formed the metrograph extension. Okay, and so the two limits that we want to demonstrate are equal for the metrograph IIC are the following. So we're going to introduce both of the limits individually, and then we'll compare them side by side and talk about what we can do. So what we want to look at is that the first definition that we can define for one of the limits is that we want to look at Kesten's incipient infinite cluster for the metrograph Gaussian-free field in 3 dimensions from conditional crossing probabilities of level set percolation of the metrograph GFF at the critical h is equal to 0 threshold. And we introduce this quantity that is given in definition 9 of the upcoming project because it very serves as a metrograph Gaussian-free field analog to one of the definitions that Kesten originally provided for Bernoulli percolation. So again, like we have been mentioning, is that we know about the critical parameters PC is equal to half for Bernoulli percolation, and on the other side for the metrograph extension at the three-dimensional GFF, we know about the h is equal to 0 threshold. And we know that the law of the metrograph extension of the three-dimensional GFF is dependent upon the size of the finite volume H across which we want to measure the crossing probabilities in addition to the height of the field. So we can form already about this critical height is equal to 0 threshold the following quantity. So we want to introduce for h equivalently 0 the probability, this conditional probability. So we want to look at the probability of some cylinder event occurring that we introduced from the previous slide, but we want to condition upon the fact that we want to look at we want this cylinder event to occur conditionally upon the fact that W is connected to script B of Wn, where this is just given by some box and W is given by some point. So we want to look at whether conditionally upon this cylinder event E occurring, whether this conditioning can occur in this probability. And in the conditioning, we want the crossing event between W and script B of Wn to occur across the height greater than or equal to 0. And this is for notational convenience, we just suppress some of the parameters that are introduced in the probability measure. Namely, we don't include alpha and beta and n, in which we can just have this probability across the critical height threshold of 0 of this conditional cylinder event occurring. But besides the first limit that we have, the second limit that we can also look to define is the supercritical conditional crossing probability for level set percolation connectivity events of the metric graph GFF about the critical h is equal to 0 threshold. And this establishes another analog in the context of the three-dimensional metric graph Gaussian-free field that was originally provided for Bernoulli percolation, and it fits within the general line of arguments and background that we've been providing because we want to demonstrate that there are two limits and that they are equal, which would show to us that Kesten's incipient infinite cluster exists. So what we want to look at is that we want to see for some sequence of heights hn that is approaching 0. So we want to take some sequence of heights, and in the same way that we looked at how Bernoulli percolation approaches the critical parameter of PC being a half, we can also look at the process of taking a sequence of heights and having them approach the critical height h is equal to 0 threshold. And what we want to do is we want to look at the following probability. So instead of the probability just being dependent upon some height h that was given from the threshold that we provided in the first limit from Kesten's incipient infinite cluster, we want to instead look at the probability of alpha and beta of n of h of n. So we want to introduce some sequence of heights h of n that is dependent upon whatever size of the finite volume we are measuring the connectivity across. And we want to look at this conditional crossing event occurring, in which we want to look at a cylinder event occurring conditionally upon the fact that the cardinality of the clusters, which is given for some v in the vertex set of our lifted metric graph, is infinity. So we want to basically see whether when we take this supercritical sequence of height parameters, whether the probability of this conditional crossing event occurring would occur. And what we want, and again, as we had mentioned for the previous limit, just to make the notation a little bit lighter, we can suppress the alpha and beta and the n. So in the final quantity that's given here, we have the limit as hn tends to 0 from above. So saying that we have some supercritical choice of height parameters that approach the critical threshold of h is equal to 0 from above, of p of hn of this cylinder event occurring conditionally upon the fact that the cluster that's centered at some little v in the vertex set of our lifted graph is infinite. And as we had alluded to previously and been mentioning, the existence of Kesten's IIC for the metric graph Gaussian-free field in 3 dimensions would assert the following. We would want to show and demonstrate that these two limits are equal. So one limit is given by a conditional cylinder event that's taken precisely at criticality at the critical threshold, h is equal to 0 threshold of the metric graph Gaussian-free field, whereas the other limit that we're having is dependent upon a choice, a sequence of supercritical height parameters that approach this critical h is equal to 0 threshold from above. And the difference, and there's also, but besides the dependence upon the law of the metric graph Gaussian-free field on the heights h of the 3-dimensional metric graph extension, we also do introduce some slightly different conditioning for the cylinder events in each one of these crossing probabilities. And so, in order to establish the equality between the two limits provided in the previous slides, we have to make use of the following assumptions. For one, we're just going to state the assumptions first in the simplest case for Bernoulli percolation, and then we can draw our attention to the listener to the upcoming paper in which more of the details are provided. And so what we want to look at is P of P, which is given by the probability measure for Bernoulli percolation, and the two assumptions that Basu and Shapotnikov provide in their 2016 paper states that there is a uniqueness of the infinite open cluster in which, in the context of Bernoulli percolation in 2 dimensions, it states that for the parameter P, which is contained strictly between 0 and 1, there exists almost surely at most one infinite cluster. And the second assumption, which is a bit more technical, that I haven't included all of the background about how all the symbols are defined, is quasi-multiplicity of crossing probabilities, which, roughly speaking, in the case of Bernoulli percolation, is lower bounding the probability that x and y are connected within some subregion of the squared lattice, which is bounded below by some strictly positive constant c star, as well as two other connectivity events which are taken under the Bernoulli percolation probability measure that are also under parameter p, but instead are connectivity events between either x or y to S, which is given by the boundary of a finite volume. In establishing that the quasi-multiplicativity of the crossing probabilities, either for the three-dimensional matrix graph GFF or for the Villain model, is dependent upon the following. First of all, whenever we're looking to construct the IIC or an IIC type limit, we have to look at the underlying dimension in which the IIC is constructed, in which from the two models that we have been describing besides Bernoulli percolation, in which the IIC was first constructed in 1986, the metric graph GFF IIC dimension is 3 because we want to look at, we've been mentioning properties about three-dimensional level set percolation at criticality for the GFF, as well as, on the other hand, the IIC type limit for the Villain models too. So the dependency of the critical thresholds for the parameter introduced in each model is of importance, in which for the metric graph GFF, the height threshold can draw our attention towards signatures of criticality, while for the Villain model, other parameters will come into play, which we'll mention in our brief introduction of the model and how it relates to our discussions of the IIC construction. So before we transition to the Villain model, we want to also conclude our discussions of the three-dimensional metric graph GFF by providing an overview of how we would construct the IIC for the metric graph GFF in 3 dimensions in light of the two-dimensional construction for Bernoulli percolation. So from part of these themes that we've been establishing comparisons with, we've seen from the Bernoulli percolation incipient infinite cluster from the abstract that's given in Kesten's 1986 paper that it's demonstrating that items 1 and 2 are equal, which we distinguish between one probability being taken at the critical parameter and another probability in the second item being taken as a function of a supercritical parameter above the critical threshold for Bernoulli percolation on Z2. And from this lens of criticality, we know that the three-dimensional metric graph Gaussian-free field can be analyzed by looking at an equality between the two limits that we discussed and motivated earlier. So this is just to say that we can look at constructing the IIC by taking either into account the dimensionality of the incipient infinite cluster and how it relates to the model that we're looking at, as well as how changing different parameters that each model is intrinsically dependent upon would impact our construction of this object. And in summary, thus far, I wanted to provide these brief remarks in words before we transition to the Villain model, which is the final section of the presentation. So in words, what we have done revolves around establishing comparisons between the three-dimensional metric graph GFF and the two-dimensional Bernoulli percolation, and discussing how criticality is achieved in both models, and providing an expression for each limit involved in the construction of the incipient infinite cluster for the metric graph GFF in 3 dimensions. And to move forward with this for the Villain model, we'll briefly draw the listener's attention to some general characteristics of the model, from which more details about the construction of the IIC can be viewed in the upcoming paper that we have been mentioning. So we can introduce another open problem for constructing an IIC type limit for the Villain model, which is based upon this paper. There's actually a more recent update a few days ago, or exactly today, on the random clusters in the Villain and XY model due to Professors Dubedat and Falconet. And in this paper, they begin by defining the Villain model by introducing the Hamiltonian, in which it takes an expression of this form. We can look at the Hamiltonian, which is a function of the angles theta x and theta y, and it's given by a product of a minus beta, which is a minus inverse temperature times this quantity squared, which is a theta x minus theta of y plus 2 pi n. And from this Hamiltonian that we use for the Villain model, we know that the spin space from which we can sample configurations that we would like to look at this probability measure under are u of x, where x is one of the vertices in the underlying graph whose structure we had introduced before when discussing the metric graph Gaussian-free field. And this is given precisely by a quotient of r with 2 pi z. So this quotient modulo 2 pi z is making apparent the fact that the Villain model configuration that we can sample from the Villain sample space is dependent upon some theta of x term, which is drawn from the sample space of U. And theta x and theta y are strictly positive. And from the Villain model Hamiltonian, we can also define the probability measure, in which the Villain model probability measure from the Hamiltonian is given by the following expression. We incorporate a lot of similar ingredients that we use when defining and analyzing probability measures for many models in statistical mechanics, in which we first have to keep in mind what the probability measure is, in which we want to look at this boldface P, which is of the Villain model that's supported over the underlying graph script G, and we want to sample some spin configuration omega, which is subject to the boundary conditions theta. And in the paper for the discussion, the boundary conditions are always assumed, or most of the time assumed, to be theta being equivalently 1. And the probability measure itself can be expressed as the reciprocal of the partition function times an exponential minus the Hamiltonian that we introduced in a previous slide, in addition to a product measure d theta of x, where x is in V. And this is just equivalent to the Hamiltonian that we wrote in the previous slide that's evaluated against this product measure over x and V. And the Villain model can admit a different type of approximation from what's given to other models, because if we let the inverse temperature, the inverse temperature roughly approach plus infinity and become very large, instead the exponential part that's in this Hamiltonian can be approximated with minus beta over 2 cosine theta x minus theta y. And the Villain model from the probability measure and Hamiltonian and boundary conditions that we have been introducing admits the following connectivity events, in which we want to look at how we can quantify how the probability of an event occurring that will connect 2 points x and y, where the connectivity event is taken over some subset U that's strictly contained within the Villain model sample space that was given by r of 2 pi r mod 2 pi z. And this is just demonstrating that we can make use of connectivity events, boundary conditions, and looking at the ambient dimension in which we would like to construct an incipient infinite cluster, which directly applies to the remarks that we had established for Bernoulli percolation from Kesten's 1986 work, and how the thoughts surrounding the criticality that the Bernoulli percolation exhibits can also be viewed to study critical behavior of the Gaussian-free field and also of the Villain model. And the Villain clusters are also another object of interest, because it helps establish another component that we need to use to make use of in constructing the incipient infinite cluster. And the Villain cluster is given by the collection of all points G twiddle, where in order to define the extended Villain clusters, we have to define the extended Villain model, which is equivalent to a cable system representation, just like how we had constructed the metric graph Gaussian-free field from the regular Gaussian-free field. And from these clusters, we can make use of these objects to also define the two counterparts for the metric graph Gaussian-free field initial, or IIC, and also another counterpart for the Bernoulli percolation IIC for the Villain model as well. And by incorporating information from the theta interactions that we've been describing, which are defined in the Hamiltonian for this model, which we incorporate to define the probability measure, an IIC type limit can also be constructed, which is related to the following two ratios. We can either look at the expectation of the IIC with respect to the Villain model IIC of an exponential of I k theta naught for k is equal to 1 or k is equal to 2. And additional details are provided with regards to this construction in other results that are mentioned in Professors Dubedat and Falconet's paper in the upcoming work. And so as to give some conclusions, we described the metric graph GFF. We introduced some 1986 arguments due to Kesten for the two-dimensional incipient infinite cluster, and we provided expressions for the two limits of the metric graph GFF. And so we discussed the Villain model and characteristics of its IIC type limits, and we attempted to draw the attention of the listener to different facts of criticality and different signatures of criticality that a couple of different models in statistical mechanics can satisfy, and how one could think to make use of and apply Kesten's arguments from his 1986 paper in different contexts, in the context of two different models. And thank you very much for your attention.